Right, what you're looking at right now are some examples, or will be some more examples of how to find max and min. I've put a whole set of worked examples for you as well, so maybe I should show you that first. If you go to Canvas, you will see a new link, help with max, min and Lagrange multipliers, homework. And click on this. And you may or may not be seeing this. I'll just tell you what you will see when you go in. It's basically I put together some PDFs. This one is on finding max and mins. This particular one is I've worked through question 9. This is max and mins when there's a constraint. Question 12 is a closest point. And question 15 is a question to do with finding the minimum surface area for a box. And if you scan through it, it's quite a long question. And then we finish with some notes I've got in Lagrange. So they're basically going to help you with the last 2 sections. So hopefully that will be some extra help for you, because we do have a kind of time constraint, and I'm trying my best to compromise between time and doing some questions. So what I'm going to be doing now is I'm going to do a basic one. I'll do this one. This one is not on the notes. I'm then going to talk through the other ones so that at least you'll have a video, but you shouldn't need to write down any of the working. Essentially, if it's on a video, you can just go and look at the video. So your notes might be better suited to you just writing extra comments that are there to help you. So we're looking at how do you find, in this question anyway, how do you find the maximum value of this function, the minimum value, or the coordinates of a saddle point if it has one? Well, the question?
Didn't you do this yesterday? I have notes on it.
I did, but I think I got it wrong, or I didn't finish it. Did I do it wrongly yesterday or not? Because I got an email saying that it was confusing because I did that. I don't need to do this one if you feel this one's cool. Are we good with this one, or you want me to go through it as if we haven't seen it before?
I'm all for going through it.
Okay, then we are doing it.
I think we got messed up yesterday.
Right, so this time I'm trying not to get messed up, right? So this is going to be the correct version of this question. And I'm going to be a little bit slower because I'm just not very good at being careful. So as I'm doing it, shout at me the minute you see a mistake. Shout at me if you think it's a mistake, and then if it ends up not being, I don't have a problem with that. So this fella is 9x squared. This guy is -9, and this guy here is what? 9y squared. Agreed? And we're going to find out when that will be 0. And hoping I've actually written the right question down, but never mind, too late now. And if you do a partial derivative with respect to 0x, this is 0, this is 0, and this guy just becomes 18xy. Looks good. So I'll call this equation 1, call this equation 2. I'm trying to find out values of x and y, so they have to be together, that make both of these 0 at the same time. So I'm going to focus on this one here. One solution I will get is x equals 0, right? That would make this 0. And the other one would be a different situation when y equals 0. So let's focus on the x equals 0 situation. Well, if you go back up here to this equation, equation 1, but you replace the x with 0, what you end up with is essentially 9y squared, take away 9, which is 0. And I'm going to cut some corners here, but I think they're pretty obvious. Would you agree plus or minus 1 for y will solve that issue? So that means I have 0, 1 and 0, negative 1. So here are two essentially critical numbers. Now, what about y equals 0? Well, if you go to equation 1, but you make y equals 0, what do we get? Well, we get 3x cubed, take away 9x. If I pull out...
Isn't that your original equation?
Good, thank you. See? Catch me. This is equation 1. I'm going to tell you in a few seconds. I'm going for the sympathy factor in a few seconds. If you take this one and you make y 0, you will get 9x squared take away 9, which is 0. And that ends up being x is plus or minus 1. And that gets me 1, 0, and that gets me negative 1, 0. So essentially, we have 4 combinations of x and y that have the property that these two derivatives are both 0 at the same time. We call these guys critical numbers. Now, the function we're dealing with, this guy over here, what we're now going to have to do is we're going to have to find out, is it a local max, a local min, or even a point of inflection? To do that, I have to calculate D. So I'm just rewriting this fella. You probably don't need to, but I'm trying to reduce my mistakes. I get that guy. I also get nothing. I also get that guy. And if I write down f of y, which is this fella, then f of y ends up being this guy. So I'll try and put circles around the people that we need to know. We need to know this fella, we need to know this fella, and we need to know this fella. Because D is giving us that second derivative multiplied by this second derivative, take away this guy squared.
The first partial derivative of x, wouldn't that be positive 9y squared?
Which one?
The first partial of x.
This here? Oh, you mean over here?
Yeah.
Thank you. That's just a mistake, but thank you. You're doing your job. Second derivative of this guy. Well, you choose each one of these fellas and you find out what D is. I'm going to pick, who am I going to pick? I'm going to pick this one. So at 0, negative 1, this fella will be 0. This fella will be negative 18. This fella here will be 0. Is that right? 18x. Yeah, 0. F of xy, negative 18, 0. Okay. So D is going to be 0 for that piece, 0 for that piece, take away negative 18 squared, and that becomes eventually a very big negative number, which is negative 324. Mistake. What have I done? Oh, I did something right for a change. According to the test, remember the test that said if D is this and so on. If D is negative, doesn't that typically mean we probably have a saddle point? Agreed? When D is negative, we probably have a saddle point. Can you trust me? I went to the software and I looked at it and it was a saddle point. Now, what you then do is you go through every single one of those combinations and you will discover whether it's a max or a min or a saddle point, and you will fill it in. And I think I have it. I do. If you want to actually see what that thing looks like, it looks like this fella here. So if I rotate it a little bit, maybe here, can you see a little saddle point here? See another little saddle point here. You see a very thin, skinny maximum here, and right down over here, you can see a minimum. So I can tell, looking at this shape, there's going to be one max, one min, and two saddle points. So we've just found one of the saddle points. Now I'm going to go for the sympathy factor, which I'm sure I've told other people so they're kind of aware of it. I have only got one good eye. I only see out my right eye, my left eye's shut, which means I have a really big problem with certain things. But one of the things I have a problem with is scanning, which means as I scan horizontally, having one eye, it tends to drift. So it's not that uncommon for me to read this when I think I'm reading that, which actually happened. So all other mistakes are just caused by me being old and careless, but scanning mistakes are one of my favorites to do. And I have other sorts of weird issues, like parallel parking is interesting, amongst some other things.
I mean, that one's pretty inconsequential.
What, the scanning one?
No,
In the big
parallel parking.
Okay.
No one does that.
Well, you've got machines and cars now that do it for you. I think they must have been thinking about me when they did that. Right, now that one was actually written with some fixes, I'm glad to say. Here is one of the questions that is online, so you don't need to write all of this. I'm just going to talk through it. One of the advantages is when I do one like this, I fix my mistakes as I go, so you end up only seeing the right version and not the corrections. But in this particular kind of question, you've been asked to find only an absolute max or min, but there's some constraint, and the constraint is very often written in this type of format. So what do you do to solve it? Well, you take your function and you find its partial derivatives and you set them equal to 0. And in this case, there's not much of a solution. It's at the origin, right? X is 0, Y is 0. You get a place where a max and min must live, or could live, let's phrase it that way. In this case, you then evaluate the function, which is the original, and you get 1. So the first part is kind of, you do what you always did, right? But you don't find D. All you do is find critical numbers and then the value of the function at these critical numbers. Because in these questions, we're only interested in the absolute max and min, not necessarily anything more than that. Now, what do you do? Well, now you look at the constraint. In this case, the constraint was a combination of x squared plus y squared less than or equal to 1. And in this particular case, we don't need to worry about the values inside the constraint because that was taken care of here. So what I'm doing is I'm taking this equation, and this one we got wrong, so I'm fixing it. You've got a y squared is 1 minus x squared. Then what you do is that you use the constraint function, whatever this is, and you use it to take the original two-dimensional function and convert it into only having, say, x's or y's. It really doesn't matter which you do. And this is what the function looks like. And basically, I replaced the y squared with this fella and y squared squared because it was that fella. You end up with this fella. Now, at this point here, what you need to do, and I didn't do that last time, is you just need to find where the max and mins of these guys are. So this is actually a one-dimensional function now. It's really that function. And how do I find out where the max and mins are? I do what I did in Calc 1. You differentiate, you make it 0, you solve for x, and it looks like 3 different x's. Now, when x is equal to 0, since y squared is 1 minus x squared, y squared ends up being 1, and that means that there are 2 values of y that match that. So when x is 0, I could have 0, 1 as a choice, or 0 at -1. And at those 2, I evaluated the original function, and it ends up being 2 in both cases. Another possibility comes from this fella. Couldn't x be a half? Well, if x is a half, y squared is 1 take away x squared. That makes y squared 3/4, which makes y plus or minus. Oops. Thought I'd caught them all, but I missed one. Not a biggie. Plus or minus √3/2. And you evaluate the function at a half √3/2, which gives you this number. And you evaluate it at a half -√3/2, which gives you the same number. And then there's a last possibility. X could be -2, but when you plug in y squared here, you get a negative number, so that makes this not usable. So if you scroll through all the answers that we had, our first answer was 1, and that's the smallest of the lot. And the biggest answer was 2, happened here, and that's the biggest. So the absolute maximum of this function is 2, and the absolute minimum is 1. Now, if you want to visualize what the heck is going on here, how can we have a surface with a constraint? I want you to imagine, and I'll try and actually put this onto GeoGebra in a minute, that this is your basic surface, z equals. X squared plus y squared less than or equal to 1, isn't that on the floor, and it's basically a circle? The origin is the center and its radius is 1, and you just go up vertically. So you're just taking a piece of the surface and then you're only using the bit that's above, in this case, a cylinder. So let's see if I can make that happen. I'm in GeoGebra right now, so I'll wait till I've got it all down before I get and switch it round, just in case Zoom gets annoyed by using a piece of software like this. So I'm just typing in the original function, which is 2x cubed plus y to the 4 add 1. And then I'm going to type in x squared plus y squared. And I'm just going to put in the equals one. Equals 1. And let's have a look at this thing. Now, it didn't. I mean, it is correct, but it isn't very easy to see what the heck's going on. Do you notice that my circle looks like an ellipse? Can you see that? And the reason it looks like an ellipse is because it has, the axes are not balanced. So I'm not convinced this has been particularly helpful. Should be able to choose a different scale. Can I do that? No? Okay. Well, sometimes GeoGebra helps. I don't think in this particular case it has. But can you imagine visually? I could probably draw it.
There's also Calc Plot 3D, which can also do it easily.
So, say that again, Calc Plot 3D? Yeah.
It's another software that lets you graph.
Yeah, so that one might have done it. Can you imagine, this is me trying to show you what the heck's going on. Can you imagine x squared plus y squared just generates a column? And then you have your normal surface doing its thing. And when these two things interact, can you see it's a bit like somebody getting a tin can and cutting a piece of wavy cake, and you're just trying to find the highest and lowest part on that wavy piece of the cake. So you're just imagining it would cut the piece like this, and you would be trying to find the biggest and smallest. Okay, that was 9. That's how you do every single absolute max and min question. You find the first derivatives with respect to x and y, and you find a critical number, and that might be one of your points. You then use your constraint equation to change one of the variables in terms of the other, so that your original equation can be written in terms of, say, x, and then you use Calc 1 to find those critical numbers. And then you put that package together. You might have 4 or 5 different places, but whatever one gives you the biggest value is your absolute max, and whichever one of those gives you the smallest value is your absolute min. And this one is online, so I'm not even going to attempt to do this fella on GeoBra. It's taking up too much time. But imagine that you've got a plane or a surface that looks like this, and you want to find the closest point to it, the closest to the point 3, 4, 5. So some point in this surface is going to meet up with this guy, and it's going to be the shortest, closest distance. So what you can do is you can imagine a general point on this plane. I'm going to call it Q. So can you imagine this is the plane? And I'm just choosing a random point. I'm calling it Q, X, Y, Z. And then up here, we've got the point 3, 4, 5. And what we're going to do is we're going to find a formula that tells us what the difference between the distance between those 2 points is. And that's basically what this is doing. Isn't this the distance formula squared? Not x take away 3. So this is your optimization function. What's the difference here? The difference is that you've got 3 variables, which we don't want. But we take the fact that we know that this fella is on a plane with this equation. So if you rearrange it, can't you say z in terms of x's and y's? So this guy becomes him, who then becomes him. So d squared is now this equation. At this point onwards, you're really just repeating yourself. Think of this as a function called f of xy. And our job is to find max and mins, or in this case, minimums, because we want to find the shortest distance. So we got this fella. If you do a partial derivative with respect to x, you get this. You set it equal to 0. You take a partial derivative with respect to y, you set it to 0, you get this equation. That means we now have 2 equations, nice easy equations. If you solve them, I believe x is 11 thirds, y is 10 thirds, and z is 17 thirds. Now, in this case, you don't need to go any further. Since there's only one solution, it must be the one you're looking for. So x is 11 thirds, y is 10 thirds, and z is 17 thirds. That must be the closest point on the plane to what you're doing. So this question, how to find a point on a surface that's closest to, say, 3, 4, 5. This is your general approach. Find the distance formula squared. Find a way of replacing one of these, typically z, in terms of x's and y's, so that your equation that you're going to optimize is this one. Now, when you take this equation, you then just find partial derivatives with x's and y's, set them to 0 and solve. And if there's only one answer, you've got it. And if there's 2 answers, it just means that the surface, and can you imagine the surface would look like this? And you've got a point here. Well, that'd be a bad choice, but couldn't you have a point here and a point here that are both closest, but at different locations? So you might get 2 solutions sometimes. And if you do get 2 solutions, it will be the answer. It just means there's 2 of them. There we go.
Yeah.
Now, this is a new guy. We never did this fella. This is also online, and there's another version of, a different version of this online as well. So although I'm going to talk this one through, and I'm going to do it a lot slower than the others, it is online, so you don't need to frantically write it down. You can print this out yourself later if you feel like it. It's the exact copy of this, right? It's a PDF. So the problem was find the dimensions of a box with a volume of 8,000 cubic centimeters that has the smallest surface area. And the question says, let X, Y, Z be the dimensions of the box. So I've decided to call this X, this Y, and this Z. What shape do you think this box is going to be the most efficient and therefore minimum surface area?
Cube.
It's going to be a cube. And it is going to be a cube. But we have to prove it, right? So we're going to do the math to get there. It's very similar. Can you remember the calc? Oh God, where was it? The calc 1 questions where you had a box and you tried to find the minimum surface area. Remember those guys? This is like the grown-up version of that. So a little picture to help me. The optimization function is just the function that we're trying to, in this case, minimize. So since I'm trying to find the smallest surface area, the optimization function I'm calling S is the guy that you need. Now in this shape here, that face and that face gives you 2 XYs. This guy is YZ, or one at the back, YZ, and the top and the bottom give you that. Can you see then that you get 2 of these plus 2 of these plus 2 of these? That's the surface area of that shape. It's basically made up of 6 rectangles, 2 of these, 2 of these, and 2 of these. So far, so good. Now, what else do I know? Well, technically, there's a constraint here. The constraint is that you know the volume is 8,000. So doesn't that mean X, Y, Z has to equal 8,000? And that means I can rearrange this equation to get Z in terms of X, Y, which is what we kind of like to do in these questions. And it ends up being a rather ugly 8,000 over X, Y. So far, beyond the thought process of how we're approaching this problem, get the surface area, use the volume to figure out what Z is in terms of X and Y. Can you see what I'm now doing in the next piece? Is I'm taking my formula, this guy here, and I'm replacing that Z with this fella and this Z with this fella. And then I'm tidying it up a little bit, right? Cancelling out some X's and multiplying by 2, cancelling out the Y's and multiplying by 2. So our optimization function, our surface area function, do you see it's now got 2 variables, which is what we need, right? Now, at this point onwards, it doesn't matter that it's a box. Aren't you going to go through the same process of finding the first derivatives, making them 0, and trying to solve, right? So let's see what that looks like in practice. Here is that formula, right, for the surface area using only X's and Y's. If you do a partial derivative with respect to X, you get this guy, which I'm now rearranging to be that guy. Do you see that I had to convert especially this fella into a negative power just so I could get to the derivative? Now, if you do the other guy with respect to Y, actually, now I think about it, couldn't I have skipped that entire line and just used this to get that because of the symmetry? I'm just saying, couldn't I have taken this answer and decided what that was without the work? So I now have the 2 partial derivatives. I'm going to make them 0 and try and solve what values of X and Y are both of these going to be 0 at the same time. Yeah. So that was the first one. I just rewritten it, calling it equation 1. That was the second relationship. That's basically Sx and that's Sy. Now, how am I going to solve them? There's no one method for solving these. It's really whatever you get, you try and figure out some way around it. And one common technique doesn't always work, is substitution. In other words, pick an equation, for instance, take equation 1, and rearrange it so that y is in terms of x. And then you can plug that guy into equation 2. So I'm going to substitute y equals for this. So it's going to be 2x take away 16,000 over that guy. Now it gets messy. 16 over y squared becomes 16,000 over ugly fraction squared. Ugly fraction squared gets you 64. Fix it. Million over that guy. Oh, we're cool. I did fix it. I just didn't tear off the old page. So this is the correct version. We already got this. If you plug it in here, it's 16,000 over that number, right? That's the number I should have fixed. So it is done. Cancelling it down, you get to here. Pull out an x as a common factor, you get to here. So 2x, take away this ugly guy. The x to the 4 comes in the top. The 16,000 and the 64 million thing cancel out, and that's where that 4,000 came from. And it's still equal to 0. So I went from this line to here. Now, if you pull out x as a common factor, you get this. X could be 0. That's a possible choice. But since y is 8,000 over x squared, isn't 8,000 over 0 a non-starter? So no good. If you look at this then, you're trying to find a value of x that makes this 0. So you're trying to solve this as 0. And that ends up being, 20. Right, x cubed is 8,000, that makes x 20. And if x is 20, isn't y 8,000 over x squared? So that makes y 8,000 over 20 squared, which makes y 20. And isn't z this ugly fraction, which means it's equal to this, which is also 20. And right at the beginning, we went and said, it should be a cube, 20 by 20 by 20. So this guy is there. This page shouldn't be there. But it works, right? So when I'll probably go into that PDF and kill off that bad page if it's there. I may not have copied it as a PDF. I think it gets stuck in when I made a mistake. Whew.
Yeah, that extra page is in there.
Okay, so I need to kill that page off so it isn't there anymore, right? But I can do that pretty quickly. So probably not in the next few hours because I have classes to teach, but I will do it. Do you feel comfortable the process of how you're going to do the 3 kind of situations that we've covered today? You feel good about that? And that's pretty much what that section is about. So that brings us now to a new guy in town. And what we're going to deal with, I'm just closing off some excess screens here. Okay. What we're going to deal with, what's the number for this darn thing? 14.8, yeah. So our last section, what we need to do to be ready for our test is going to be Lagrange multipliers. This is a technique for finding maximum and minimum, absolute maximum and minimums with constraints. So, right, it's the same kind of question that we did a kind of very algebraic way, right? But this guy Lagrange came up with a really cool piece of magic that allowed us to solve absolute max and min questions subject to a constraint in a much nicer version. It is going to be a little bit weird, and it certainly might not make to be intuitive, but can you just trust me, it works, and we like things that work, right? So in general, you're going to have a function f of x, y, let's say, and I'm not going to create one of these. I'm going to go straight into WebAssign and pick one. And there's a really good idea why I do that. If you pick a question from the WebAssign, isn't it going to come out as nice numbers? If I just randomly pick some questions, I'm going to have 17 over the cube root of 412 and some really not very pretty results. So I'm just being lazy, I guess. Okay, so let's suppose I have a function 10x plus 8y, and the constraint is that x squared plus y squared has to equal 41, right? And we're being asked to find the absolute max or minimum of this function subject to that constraint. Now, if you imagine what that might look like in 3D, won't that basically be z equals 10x plus 8y? Great. And if I rearrange that, isn't it 10x plus 8y take away z equals 0? So what that tells me is it's a flat plane, right? Now, x squared plus y squared equals 41. I'm not impressed by the 41 bit, but wouldn't that be a circle going upwards? So can you imagine what would happen there would be an ellipse probably? You know, if a sloping plane meets a vertical circle, wouldn't that cut be an elliptical cut? And what we're after is the highest point and the lowest point, right? The max and mins. Now, what does Lagrange tell us? Well, you call this guy here, right? This whole thing here, you call him g of x. And you typically call this guy f of x. And according to Lagrange, what you need to do is you need to solve when is the gradient of f equal to lambda times the gradient of g. Now, lambda is a constant, it's a fixed number. And we will use that relationship to actually find coordinates of places where the absolute max and min will live. Okay, if I asked you to find delta f, wouldn't it simply be the number 10 and the number 8 in this case? Lambda is there. If I asked you to find delta g, remember this guy here is delta g, right? This is g. Won't that be 2x comma 2y? So that's typically going to be the first line of your working. This is a very simple question. They get much more messier as time goes on. Now, from here, you set up 3 equations. You match that this has to equal that. So that means that has to be true. This has to match that. So that makes that has to be true. And your third equation is going to be your constraint equation. So you are going to have 3 equations. I'll call them 1, 2, and 3.
Wouldn't the second equation be 2 lambda y instead of lambda y?
Yes, it would be. Right. Now, how do you solve it? The first one is let lambda equal 0. Now, you check, I guess is a better word. You check for lambda equals 0. 99 times out of 100, lambda equals 0 won't work and it doesn't generate a solution. But the one time you don't check it is the time you should have, because that way you end up missing a possible solution, a possible critical number. So if lambda was 0, wouldn't equation 1 say that 10, which is 2 times lambda x, should be 2 times 0 times x, which is 0? And would you agree that that is a non-starter as a possible solution? So just as I would expect, lambda equals 0 ain't going to happen, right? Then you move on to these guys. And one of the most common strategies for tackling this type of question is to take equation 1 and divide it by equation 2. Now, equation 1 has got two sides to it. So basically you go 10 over 8 is 2 lambda x over 2 lambda y. Now, normally in mathematics, that's a very dangerous thing to do. Why? If one of these was 0, wouldn't that not be true anymore? But the lambda equals 0 has been checked, so we know that lambda isn't 0, right? So that's why we do the lambda 0 check as well. Now, if you cancel that down and simplify it, doesn't this guy become 5/4? And I believe this guy becomes x over y. Great. Have you noticed that by this division process, haven't we eliminated the lambda issue? It's no longer a problem because it's gone. What we're going to do with this is you typically use it to find out what one of the variables is in terms of the other. Would you agree that y is 4/5 x? Now, how's that going to help me? You use it in equation 3. Since x squared plus y squared also has to be equal to 41, if it's a true critical number, one that we can use, that's going to be x squared. The y can get replaced by 4/5 x. And this becomes x squared plus 16/25 x squared equals 41. Have you seen, slowly but surely, aren't we getting to a place where we can actually get a number? Isn't this an equation in only one variable now? Now, if you add this and this together, that's why you choose questions from the book. Do you see that that is what you've got? Can you trust me that this fella ends up being 25? Or do you want to see a line or two where it eventually gets you 25? Can you imagine that you multiply both sides by 25 41s and you get 25?
I can see it. Yep.
Yeah, okay. Now that's great news, because doesn't that mean x could be plus 5 or x could be negative 5? Agreed? X squared is 25. That makes x plus or minus 25. Okay. Now, for each one of these, let's take x equals 5. Don't we know that y is 4/5 x? So won't that make the y value 4/5 of 5? I'll make the y value 4. So here's a guy, 5/4. Now, if you plug in x equals negative 5, won't you get negative 5, negative 4? These are the only two places that you need to go looking. So which one of them is the absolute max and which one of them is the absolute minimum? Well, don't I just return to the question, the original function, plug in these x's and y's, and whichever one gives me the biggest answer, that's the absolute maximum of that function, and I even know where it's going to happen. And if I plug the other one, I get the minimum. So let's see what we get here. for the function f of xy equals 10x plus 8y, at the point 5, 4, you get 50 plus 32, you get an answer 82. And at the point -5, -4, I believe you get -50, -32, and that's -82. So see that guy there? He's got a z value of 82. That's the biggest value the function is. See that guy down there? He is -82. I can even tell you the coordinates. 5, 4, 82. -5, -4, -82. Do you see we even know the coordinates of these points if we were asked it? Now, the approach to this question is, I don't think it's that intuitive. I mean, it seems unusual that the relationship that we used with delta G being equal to lambda, delta F being equal to lambda delta G would solve the problem. But it does. It's kind of nice. Right, here goes. This one is going to be a little bit quicker, but I'll try to cover as many situations as I can. Here is optimize max and min, and the constraint in this question is that 4x squared plus y squared equals 8. So this guy is my g of x, essentially equal to 8. So gradient at f is lambda, the gradient at g. You differentiate this with respect to x, you get y. If you differentiate this with respect to y, you get x. You do this guy, you get 8x. You do this guy, you get 2y. A little bit quick, but you with me? We're good. Now you do the matching then. That makes y equal 8 lambda x. That makes x 2 lambda y. Call that equation 1, call that equation 2, and my constraint function, that's going to be my third equation. Okay, going to talk through the lambda 0 situation. If lambda was 0, wouldn't equation 1 say that y would be 0? Yeah, it could happen. If lambda is 0, wouldn't equation 2 make x 0? That could happen. But is x 0, y 0, does it fit the constraint? So, ain't going to happen. Right, but we had to check it. Right, let's do the equation 1 divided by equation 2 trick. That's a kind of guaranteed process, right? You do that. In this case, we're going to have y over x, right? Y over x equals 8 lambda x over 2 lambda y. And I do have some, not this one, but I do have some examples of this online for you as well. Now, if I tidy it up a little bit, can't I cancel the lambdas and I can reduce it a little bit and I get that? Now, if you cross multiply, do you notice that y squared can be 4x squared? Agreed? Now, can't I use that in the constraint function? In other words, replace the y squared with 4x squared. So instead of the constraint function being that, it's now 4x squared plus a y squared, which is also 4x squared. That gets me ax squared. That tells me that there are two choices for the x's, right? A +1 and a -1. Okay. If x equals 1, then since y squared is 4 times x squared, doesn't that make y squared 4? But doesn't that generate 2 answers for the y? So this generates these two, that means that there's two critical numbers. X is 1, y is 2, x is 1, y is negative 2. If we take x equals negative 1, which is the second possibility, and we use it here, actually not much different happens because negative 1 squared is also 1. And so we end up with the same two choices of y, which now means that we have that guy and that guy. So 1, 2, 3, 4. Now for each one of those 4 guys, we then evaluate f of x, right? F of xy, which is that guy, right? Okay, let's see if I can do that in my head. 1 times 2 gets you 2. 1 times negative 2 gets you negative 2. Negative 1 times 2 gets you negative 2, and negative 1 times 2 gets you 2. So won't these two guys be the absolute maximum, and it's worth 2? And won't these two guys be a shared absolute minimum, and the value is negative 2? So this function, with the constraint that 4x squared plus y squared must equals 8, the biggest it'll ever be is 2, and the smallest that will ever function will be inside that constraint is negative 2. And I saw